Today is the day you finally sit down and make your first game. Was that scripted and awkward? When I launched this channel, I started with a 6-video series on how to make Snake and Godot. And just for funsies, I've cut that 90-minute series down to a tight 1-hour course that will take you from zero to game dev in an afternoon. Thought I was going to say from zero to hero, didn't you? I'm better than that. I've been making games for over 20 years, and I still love it as much today as the first day I started. So what are you waiting for? Let's get you started right now. Since most games are built on the same fundamental building blocks, we can use a simple game like Snake to make it easy to demonstrate and recognize those blocks without the game itself getting in the way. Let's get started. As you can see here, I've got an empty Godot project set up, and the very first thing I'm going to do is just create our gameplay scene. I'm going to rename this to gameplay, and then we're going to save it. We want to save this in our gameplay folder. By the way, I've set up a couple of folders off camera that I know I'm going to need in just about every project. We'll create a couple more together along the way. The next thing we're going to do is attach a script to gameplay. We're going to leave it named gameplay. And this is going to be where the majority of our game logic lives. We're going to give it a class name of gameplay. The first thing we're going to do is work on detecting user input. From within our process function, we can use the isActionPressed and look for UI_up. And for right now, let's just print out up is pressed. Let's test our game. You'll see this pop up the first time you run any project. It's asking which scene do I start with. Since we only have the one gameplay scene, we're going to select current. We can and will change this later. So now that our project is launched, you can see down here in our output window, if I press the up button, we're detecting that the up key is pressed. So it works. So let's go back and repeat this for each of our directions and save. Now if we test it again, you see it can detect left, up, right, and down. Perfect. Although with these print statements, we're not doing anything super valuable. So let's add a variable up here called move_dir for move direction, and we're going to store a vector2 in it. And by default, we're going to set that to vector2.right, which is the same as vector2 1, 0. We're going to default it to vector2.right because we need a direction for the player to start, and most games will start you moving left to right. So we're going to set this in here. We're going to set this to vector2.up. That's all we're going to do with user input for right now. The next thing we're going to do is create something to actually move. So we're going to create a new scene, and we want it to inherit from area 2D. We're going to base this node on area 2D because it's going to allow us to detect very simple collisions between the snake and the food that it eats, and the snake and itself. We need to resolve these angry yellow warnings. In area 2D, we'll expect a collision shape 2D, and a collision shape 2D is going to expect a shape. Let me switch back over to my 2D view. You can see when I've added my circle shape, it appears at 0, 0. The other thing we're going to need for the snake's head is a sprite so that we can see it on screen. So let's do that now. And of course, we don't have any sprites in our project yet. So let's right click on our gameplay folder. Let's create a new folder called sprites. And with our sprite folder selected, let's drag them over into our project. And just like that, we've got sprites in our game. Now we can use this Devil's Workshop logo as the head of our snake. And there we have it. Now you may notice that now that we have a sprite, I can no longer see my collision shape. Well, that's because the bottom of your scene tree is actually the top of the stack. So you can think of it like this sprite 2D is the closest to the monitor. So if I drag this up to the top of my scene tree, now I can see my collision layer again. Let's name this to head because this is going to be the head of our snake, and now we can save. And of course, we are going to need a little bit of code on this node. So let's click the attach script, create a new head script of class name head, and again save. Now if we go back to our gameplay scene, we can add that head by clicking this link button down here. That's going to allow us to bring in another child scene. Here's the head scene that we just created. Click open and it shows up in our scene tree. Now, when we run our project, very little happens, but there's the head of our snake. Let's go back and drag that into the scene a little bit better so that we can see it. Doesn't really matter where right now. Actually, since this is going to be a grid-based game, what we're going to do is go into our configuration, snap configuration. We're going to set this to 32 by 32. Then we're going to turn on our grid. And now when I drag it around, it's actually going to snap right onto the grid, which is what we want, because in Snake, your character actually moves in increments on the grid, just like this. So we'll just put him right here for now. If I click play, we've got our character here. So far, so good. Okay, so now we've got our snake, we've got our grid. Let's add some basic code to move this little guy around. So let's click on our gameplay scene, and I'm actually going to create a function called update snake, because I know eventually we're going to be moving more than just the head around, but for right now, let's just get some basic stuff on the screen so that we can feel good about ourselves. Within this script, we're going to want to reference the head. I'm going to click. Let's set this up to access as a unique name. What that's going to do is, in the event that we nest this under something else and change the path to this node, it's not going to break our onReady variable reference. Now we're going to drag this over, and this is actually going to be of type head, and we're going to go as head just to make doubly sure that all of our code completion works. Now, we don't actually have any code in our head right now, really, but for example, let's just say we created a function called say hello that just printed hello. If I come back into my gameplay script and type head dot, now you can see I'm getting my say hello. If I remove the as head, a lot of times the code completion doesn't actually work. Yeah, see? No say hello. So besides it just being a good idea to statically type as much as you can because it makes your code cleaner and easier to read, it also makes it a lot easier. Okay, we don't need that. Back to gameplay. We're going to move in 32 pixel increments because we want to stick to a grid. Before we do that, we need to figure out on what interval we want to move this snake. So I'm going to create a couple more variables, one called time between moves, which is going to be a float. We'll set that to 1,000. We're also going to need a variable called time since last move. That's going to represent how long it's been since the last time we moved. We can also create a speed variable. Set this to 1,000. That's going to allow us to increase the speed of the snake as the game gets harder and harder. So that'll do it for right now. Since the snake is going to be comprised of area 2Ds that we move around, and area 2Ds are physics objects, we're actually going to want to update them not in our process loop, but in the physics process loop instead. So what we're going to do is create a very simple mechanism in here for determining on what tick we're ready to move the snake. And we can do that by doing time since last move plus equals delta times our speed variable, and then we can say if time since last move is greater than or equal to our time between moves, we want to update our snake, and we want to reset our time since last move. We can get rid of our pass, and to show this in action, we can print move the snake. And if we run this, you'll see on regular intervals, we're getting that message. If our speed went up, let's make it say 10,000 to make it noticeably faster. You can see we're going to be moving significantly faster. So that's going to work for a mechanism to move the snake. But now we have to actually do something with the update snake method. So if we want to move our snake on every tick, we need to know the direction that it's going to move in and by how much. So we have the move direction stored up here as these vectors. And I'm actually going to type these out so you can see what these look like. So to move our snake, we can actually multiply our move direction by the size of our grid. So in our update snake function, we can do head.position equals head.position plus, then we can take our move direction and multiply it by 32, which is our grid size. So you'll see if we play this now, it should start out moving to the right very slowly. And if I press up, nothing happens. Why doesn't anything happen when I press up? Because I'm pressing up on the W, A, S, and D keys. If I press up on the arrow keys, now we're going up. If I press left, now we're going left. Let's fix that real quick. So we can go into Project Settings, choose our input map, turn on Show Built-in Actions, and find our UI left, right, up, and down. Right now, these are default mapped to the arrow keys, but we can add our WASD keys by clicking this plus button. This is left, so I'm going to press A and then OK. And now you can see that the A key has also been mapped rather to UI left. And we can repeat this process for right, up, and finally down. So now if I play this, I can move my character with the W, A, S, and D keys. So a couple of things before we move on. I want to do a little bit of refactoring. First things first, it's very possible that I might want to know something about our grid size somewhere else in the code. I also might, let's say, maybe our grid size becomes 16 or 64. I want to be able to change that in one place. And we're going to do that with an autoload file. So I'm going to right click on my autoloads folder, go to create new, make a new script, and we're going to call global. Now I can expand, open this up. I don't need any of this. We're going to create a constant called grid size. That's all we're going to do with global for right now. Now that we've created our global autoload file, we need to make it accessible to the entire project by registering it as an autoload. We can do that by going to Project, Project Settings, Autoload, and then click this folder. Navigate to our autoloads, select global. It's going to pull the name in, which is the name we want. We can click Add, and by default, it's enabled. So now, instead of hard coding 32, what I can do is type global.gridSize, which is going to be the same as 32. And that way, if it changes down the line, you only have to change it in one place. And right now, head is extending from area 2D, which means by default, it has all of the properties and methods of an area 2D. But what if we wanted head instead to inherit from another class called, say, snakePart, that both the head and the tail could inherit from, and that they would have shared functions for things like how to move them around on the grid, how to keep track of where it was on the last tick, because remember, this snake is going to move in a chain, and the first section of the tail is going to follow the head, the second section of the tail is going to follow the first section of the tail, so there's going to be some commonality between the heads and the tails. So let's make our lives easier. Let's create a new script that inherits from area 2D, and we're going to call it snakePart. And let's open up our snakePart script. Let's give it a class name of snakePart, and we don't need any of this. So snakePart itself is inheriting from area 2D, so that when the head and the tail pieces inherit from snakePart, it will still be an area 2D and have all those properties. But it's also going to have the properties that we add, the properties and methods of the snakePart class. We only need two very simple things to make this class worthwhile. The first thing is going to be a record of our last position, which is going to be a vector 2. And then we're going to need a function that defines how we move it from where it is to where we want it to be. So we're going to call this move2, and it's going to take a vector 2D called new position. And this is going to be really simple. We're going to store the last position as its current position so that we have a record of where it was before we moved it. And then we're going to set its position, the new position. And that's it. It's very simple. So we can actually close our snakePart class now and go back to the head. And instead of extending from area 2D, we're going to extend from snakePart. And you'll see that when I come in here, if I type self.move2, there's our new method that we're inheriting. Same as self as last position. There it is. Now from here, we can continue to add things to the head class that are specific to the head itself, and we can add things to the tail class that are specific to that so that they become different and discrete objects in and of themselves, but they will always share anything that we put in the snakePart. So we don't actually need any of these in the head class, so I'm going to delete them. Then we're going to go back to our gameplay script. And instead of doing this head.position equals head, so on and so forth, what we're going to do is we're going to say head.move2, and then we're going to give it this new position. So now if I click play, oops, nothing's happening. Why is nothing happening? Well, that's because we've left out its position. So what we need here is, and actually we're going to make this a little bit cleaner. So let's say variable new position vector2 equals head.position plus move direction times grid size. And now instead of that, we can put new position in here. Now if we play it, and it looks the same, but we're a little bit more flexible now. We got our character moving, but once it goes off the screen, it's gone forever. In order to make the snake wrap from the left side of the screen back to the right, we're going to build a little helper node that's going to keep track of where our boundaries are, and we're going to be able to ping it to find out whether we've gone outside of them. So let's start by adding another node 2D. We're going to call this bounds. And to that, we're going to add two marker 2Ds. A marker 2D is just going to give you a crosshair gizmo that you can drop into your game scene to visually mark something in X and Y coordinates. I'm going to name this one upper left, and I'm going to duplicate it with Command D. We're going to make another one called lower right. If I select these and go to our move tool, you can see we actually have two little gizmos that we can drag around. Here's one, here's the other. And for right now, I'm going to position this as close to the bottom right-hand corner as I can. And that's going to give us the boundaries of our screen. This is our upper leftmost position, this is the bottom right, and between them, we form an entire rectangle. Let's add a script to our bounds node. Give it a class name, bounds, and let's get references to our two boundary markers. Let's create 4 variables that we can use to store the boundaries of our game. In the onReady function, we can access the positions of our 2 markers and store those values as our minimum and maximum positions. This isn't strictly necessary because we could access these positions directly. However, these short variables are easier to type and they read more like what they actually are. The next thing we're going to do is write a function called wrapVector, which is going to take a vector 2 and it's going to return a vector 2. Now there's not very much to this function. We're going to use this wrapVector function to pass in the position we'd like to move the player to. And it's either going to return the vector that we gave it if it's within bounds, or it's going to return the leftmost x coordinate if we've gone too far to the rightmost if we've gone too far to the left, and so on and so forth. So let's see how we implement that. First, we're going to need to grab a reference to our bounds. So let's drag that in here, release with a control click, and let's force it to type bounds so that we get our code completion. Now, down here, before we set the position, let's check it against our wrapVector. So we can feed it new position. If it's within bounds, it'll just return the same position we gave it. And if it's out of bounds, it'll return the wrap position. So now, if we test our game, our player wraps nicely. Top to the bottom, left to the right. The next thing I'd like to do, because this window is a little bit gigantic, let's change the size of our game. So flipping back over to 2D, the other problem this is going to solve is, if you take a look at our marker, our game size is not exactly in 32 by 32 dimensions. So we're going to go up to Project, Project Settings, Window, and right now we've got this giant window that isn't in 32 by 32 increments. And I don't know the exact number we want, but I do know the ratio. So I can actually use a shortcut by multiplying 25 by our grid size and hit enter, and 14 by 32 to get our height. So we're going to have a window of 800 by 448. Now when I come back, you can see here we've got a smaller window size that fits directly onto the grid. And now all I have to do is move this marker into the bottom corner. And if I run it again, everything still works exactly as we wanted it to. Let's go ahead and add a tile map so we can put a very basic background grid in place. In Snake, especially when you're wrapping from one side to the other, it helps to have a visual guide to show you what row or column you're in when you're lining up your moves. We can select Gameplay, search for tile map, and we're going to want to drag this up to the top because we want it to be behind everything. And tile map is going to require a tile set. So with our tile map selected, we can click on this empty dropdown and select New Tile Set. We can click on that to change some of the settings. Now we know our tiles are 32 by 32, so I'm going to change the default from 16 to 32. Now, of course, our tile set needs some actual tiles. So let's grab in this grid. It's going to ask if we want to automatically create tiles in the atlas. For this very basic example, we can just click yes. Now I can click over to my tile map, select my tile, select the rectangular paint tool, and you'll actually need the selection tool up here selected for this to work. And now I can paint my tiles in to fit the size of our window. And let me click off of that so we don't see the orange anymore. Now when we play this, you can see we'll have a grid that gives us a visual guideline where we'll come out when we wrap around. Let's create the tail scene by going to Scene, New Scene. We'll select Other Node because you'll recall in the first video, we wanted this to inherit from Snake Part. Because Snake Part is an Area 2D, we're getting this warning that it needs a collision shape, and the collision shape, you'll recall, requires a shape. We're also going to need a Sprite 2D, and for now, let's just drag in our apple and move that back up so we can see our collision shape. Let's rename it Tail and save it in our gameplay folder. Because this inherits from Snake Part, it already has our Snake Part script attached to it. Later, we're going to want to add a little bit of code to customize the tail. So rather than using this script directly, we're going to right-click on our tail and select Extend Script. We're going to leave it defaulted to tail and give it a class name, tail. For right now, we don't need any additional code to make our tail work. But later, we will come back to the tail class and add some code that only the tail needs. We can delete this default code and save. Now let's go through a similar process to create our food. Scene, New Scene. Our food can inherit directly from Area 2D because we're only looking to detect collisions between the snake and the food. We don't need anything else special. Because we're in Area 2D, we're going to add our collision shape and our circle like we've done before. And we're also going to add our sprite and drag in our star graphic. We're going to rename this to food and save. Our food class actually doesn't need any code, so we're not going to add a script. But now that we have our food and our tail scenes set up, we can go back to our gameplay and start working on our spawner. Go to gameplay, let's add a new node 2D, call it spawner, and attach a script called spawner. Our spawner class is going to be responsible for dropping food at a random location inside of our game field. Let's start by creating a function called spawn food that we'll call each time the snake eats the piece of food that's already in our game scene. Though this spawner class is very simple, it's going to make use of a couple of very common Godot design patterns: signals, export variables, and instantiating packed scenes. When spawning a piece of food, we need a few elements: where to spawn it, or its starting position, what we're spawning, this is instantiation, and where we're going to put it, or who is the parent object of what we've spawned. We can start by creating a vector2 that will hold our spawn point. Since we need the food to appear somewhere within our gameplay field, we'll need to know the bounds of our screen, which you'll remember we've already created for the wrapping. We can create a reference to our bounds node and reuse that existing code. That's going to be our export variable. We can type @export var bounds and give it a type bounds. Now, if I click on our spawner and look at our properties window, we can see that export variable bounds here. If I click this assign button, it'll bring up a window allowing me to select the bounds object that I want to reference. Now, within our spawner class, we have access to our bounds object. We'll set it to vector2.0 to start, but we're going to end up setting each x and y position separately in a moment. We'll start by picking a random x value for our spawn point somewhere between the x minimum and x maximum from our bounds class. We can use a built-in function called randFrange, which will return a random float between two floats. In this case, bounds.xmin and bounds.xmax. To make sure our food never spawns directly on the edge of the game screen, let's add our global grid size to the minimum value and subtract it from the maximum. This will make sure that the food never spawns any closer than 32 pixels from the edge of our screen. Let's copy this line and duplicate it below. Now I can hold the Option key and insert multiple cursors, hit the Delete key, enter Y in all three places at once. Now we have our Y component with the same constraints. Now that we have the location we're going to spawn the food at, we need a way to access the thing that we want to spawn. That's our instantiating pack scenes. So we're going to create a variable called food_scene of typed packed scene. And we're going to set that to our food scene, which we can drag in. And if we hold Control and let go, we're going to get the path to our food scene wrapped in this preload function. This will preload our food seed into memory so that when we go to instantiate it, it's immediately available. Now, let's instantiate our food. Instantiating the food creates it, but doesn't add it to our scene tree. That's what we're going to do in this next step. We're going to get a reference to our parent. In this case, the parent of our spawner is our gameplay scene. We're going to call getParent.addChild and pass in food. GetParent in this case will return a reference to our gameplay node, because spawner is a direct child of gameplay. In a simple game like ours, using getParent is fairly safe because we know that our scene tree isn't going to change very much throughout the course of development. However, in a more complicated project, down the line we may end up moving spawner somewhere else in the scene tree, which would change its parent. For example, if I drag spawner into our bounds node, bounds is now the parent, and this code would mean that we would be adding our food to the bounds node, which is not what we want. But like I said, because this is a fairly simple project, we can get away with this. Before we can test this, we need to set the position of our food to our spawn point. Now we can return to our gameplay script. Let's grab a reference by clicking and dragging. Remember to Control click before you release. Let's force it to spawner as spawner to make sure that we get our code completion. And in our onReady function, we can tell our spawner to spawn food. So when we test the game, you see we get our first bit of food. Granted, when we run into it, nothing happens because we haven't written that part yet. And also, and this is the thing I wanted to show you, you'll notice that it's not nicely fit to this grid the way we would want, but that's an easy fix. Let's go back to our spawner class. Before we make this assignment, let's round down whatever random number is stored in our X and Y values so that it fits on our 32 by 32 grid. We can use this built-in floorF function that will take a float and round it down to the nearest integer. So we'll take our spawn point, divide it by our grid size. This will give us an integer representing the column that the random X value has fallen in. To convert it back into our grid size, we can just multiply it by grid size. And again, we can copy and paste and then convert this to Y. If we run our game, now the food will always fall nicely in our 32 by 32 grid. Next, let's work on detecting when the head of the snake has collided with one of the food bits. We'll start by going over to our food, and we're going to add it to a group called food, which we can do by selecting the root node, coming over to Node Inspector tab, select group. We're going to type food and add. This means that every piece of food we generate will belong to this food group. Groups tend to be a little bit inefficient, so I try to use them sparingly, but for a game of this size, this is going to work perfectly fine. Now with that added, let's come over to our head class. We're going to click on head, and then next to where we had group selected, we're going to come over here to signals. Since both the head and the food inherit from area 2D, we can make use of this area entered signal. If I double click, it's going to allow me to connect this on area entered signal to my head class. Right now, this won't do anything, but if we come in here and type print collided with area.name and run our game, see when the head collides with the food, we get collided with food. Great. So our collisions work. Now let's wire them up to do something meaningful. First thing I'd like to do is differentiate between running into food and anything else. In the game Snake, the head can either collide with a piece of food or its own tail. In the case of the food, we want to remove that food and spawn another. In the case of the tail, we've crashed into ourselves and the game ends. So we're going to run a check against this area, which is the area of the thing we've collided to. And we're going to say if area.is in group food, we've collided with food. Else, we've collided with something that isn't food. In our case, that's going to be the tail because there's only two things that we can collide with. Normally, to remove a node from the scene tree, we can call queueFree on it. So in this case, we can type area.queueFree when that collision happens, which will work, but there's a better way to do this. You'll see if I run into this, it does remove it, But since we're removing a physics object, it's generally safer to defer this call until after that physics frame completes and before the next one starts. So instead of calling area.queueFree, we're going to call area.callDeferred, and we're going to pass in the name of the function that we want to call. This is going to queue that to be freed up at the end of the physics cycle rather than in the middle of it, which can cause unexpected issues. But we can't just delete the food from the game. We need to be able to tell the gameplay scene that a piece of food has been eaten. This will allow us to cover that third common design pattern, signals. Let's define a signal called food eaten that we will use to report to gameplay when we've eaten a piece of food. To do so, we can call food_eaten.emit right before we delete this to let the rest of the game know that a piece of food has been eaten. Of course, emitting this signal won't do anything unless we tell what things to listen for that signal. So let's go back into our gameplay and connect the food eaten signal to a function that lives in our gameplay class. We can do that by calling head.foodeaten.connect, and then we're going to pass in a function that we're going to create now, onFoodEaten. We're going to get this angry warning because the onFoodEaten function doesn't exist, but we're going to create it right down here. Let's add a print statement in here for a quick test. Food eaten. If I run the game and we eat our food, you can see we get the food eaten message suggesting that we dropped into our onFoodEaten function, but of course nothing has happened because we haven't put any game logic in there yet. We're making progress. There are 4 things that we're going to do every time a piece of food is eaten. For starters, let's make sure that every time we eat a piece of food, we spawn more food so that we can keep playing. So we can call spawner.spawnFood. If I run this, when we eat food, we get more food, but you'll notice we're getting errors. And that's because we're trying to add a physics object while we're in the middle of a physics loop. We can fix that the same way we fixed the queueFree by calling spawner.callDeferredSpawnFood. And that's going to wait until this physics tick ends, then it'll add it before a new one begins. If we run and collect food, you'll see we're no longer getting that error. Great, it's starting to feel like an actual game now. The first thing that we're going to need to do is add an array called snakeParts. You may recall that in an earlier video, we decided to make the head and tail classes inherit from a base class of snakePart. That's going to allow us to store those together in this array, statically typed as snakePart. In GDScript, you can mix different types of objects together in an array, however you won't get code completion. For example, with this being a statically typed array, if I try to access a member of our snakeParts array, you'll see that I'm getting last position and move to suggested with autocompletion. That's because we've told Godot that everything that's going to be in our snakeParts array will be a member of the snakePart class, which includes both our head and our tail. Since both our head and our tail are area 2Ds, we could statically type this array as an area 2D. However, we won't be getting our last position and our move to functions. We could still call them, but Godot's not going to help us with code completion. And if for some reason we put something in that array, maybe accidentally, that isn't of class snake type, then we're going to fail when trying to call that method. Statically typing things in this way is both a quality of life thing, but it will also make our code more readable if someone else tries to come in and understand our logic. With our snakePart array in place, let's hop over to our spawner and create a function that will handle spawning our tail pieces. In a larger game, we might have one spawner for our food and one spawner for our tail, but since our game is fairly basic, it's going to make sense to put both of those responsibilities into this one spawner class. In order to spawn our tail, we're going to need a reference to our tail scene. Our spawnTail function is going to be fairly simple. It's going to take a vector2 that represents the location at which we want to spawn our piece of tail. It'll instantiate, move the tail piece to that position, and then like we did with the spawn food, it's going to add it to our parent. If we go back over to our gameplay script, we can scroll down to our onFoodEaten method and use this to spawn a new tail piece. Again, we're choosing to defer this call because we're adding a physics object. Coming back into our spawner, you'll remember that the spawnTail function expects a vector2. The location at which we want to spawn our new piece of tail will be the last stored position for the last item in our snakeParts array, which will look like this. snake parts array, snake parts.size gives us the length of the array, and we're going to subtract 1 because the array is 0 relative. This will give us the last element in the array. Since we've added a new tail piece, what we'd like to be able to do is type snake parts.push back and then add our tail piece here. Unfortunately, we have two problems. One, we don't have a reference to the tail piece that we've just created. We could set up our spawn tail function to return the piece of tail that we've created, but that would pose another issue. Since we're deferring this call, the tail piece that we'd like to add to our array won't exist until later. However, that's not a problem. We already have the tools to fix this. Let's go back into our spawner class and add a signal called tail added. And we're going to give it an argument of tail because when we emit this signal, we're going to send along a reference to the tail piece that we just created. We can add that down here by typing tail added dot emit and give it tail. Coming back into gameplay, just like we set up a connection to the heads food eaten signal, we can do the same here with our spawner tail added, and we'll call it on tail added. And now let's declare that function. We know it's going to receive a tail object, so we can add that as an argument. And then all we need to do in order to add our tail piece to our tail array is take this and move it down here. We want to add the head to our snake parts array because the first tail section needs something to follow. Did anyone spot the mistake that I made? If I scroll down here to our spawn tail call, we're mistakenly passing in the snake part object. What we want is the last position stored within that snake part. Now, if we test our game, you'll see that we do get a new tail piece at the last location of the head. However, if we continue eating food, all of the tail pieces are going to appear in the upper left-hand corner at 0, 0, because we haven't started updating those locations yet. Let's do that now. In our update snake function, right below where we move our head, we will loop through our snake parts array, starting at index 1, which is the second index or the first tail piece, calling the moveTo function on each snake part element in the array, passing in the last position value of the previous element in the snake part array. With these two lines of code, the first tail piece will follow the head, and all other tail pieces will follow the tail piece that precedes it. Let's test our game and see if our tail works. Now that we have a working tail, we need to be able to crash into that tail. Let's go back into our head class. Since there are only two things that we can collide with in this game, food or the tail, if we've entered the else condition, that means that we've collided with a piece of the tail. To notify our gameplay class when a tail collision has occurred, let's create another signal and emit it down here. Once again, back in our gameplay class, we need to tell gameplay to listen for this signal. Down here, we can declare this function. As a placeholder, let's just print out game over. Let's test this out. We doubled back on ourselves and got our game over message. To make this game a little more challenging, let's increase the speed each time we eat a piece of food. Since we set up this speed variable at the beginning of the project, the only thing we have to do is increase that each time a piece of food is eaten. Let's do that by adding 500 to our speed each time we eat a piece of food. And if we test our game, you'll notice that the steak speeds up a little bit each time. Earlier in the video, I promised that we would come back to our tail class to add some code specific to that class. Let's do that now. Right now, there's nothing here because the only code we're using is being inherited from snakepart. Let's add an export variable that's going to contain an array of textures that we can randomly pick from instead of always spawning an apple as our tail piece. You may notice that since we've added this export variable, our textures array has shown up in the property inspector. We can click on this array and add elements to it. At the beginning of the project, we imported 6 different textures that could be used for our tail. Right now, we're only using the hard-coded apple. We can fix that with this texture array. Let's add 6 elements and drag our 6 sprites in. And in our ready function, let's randomly assign a texture to our sprite 2D from our textures array. PickRandom is a built-in method of the array class that will return a random element from that array. If we test our project now, we should get a random sprite each time we eat a piece of food. Now our snake is moving more quickly with each bit of food, and the tail is looking a little bit snazzier. At this stage, our game logic is mostly complete, but we still have to create menus and a score before we can call this a fully functional game. Since we ended the last video by detecting when the snake crashes into itself, let's start this one by building the game over screen. We're going to use a node that we haven't used yet. Select Other Node and search for Canvas Layer. We'll start by adding a panel. This panel node is going to serve as the background for our menu, but it's also going to define some layout properties. We'll start by setting this anchor preset to full rect, which will make sure that it takes up our entire screen. In the inspector, let's expand the visibility section. Click on Modulate and drag the alpha down. This will make our background a little bit transparent so we can see through to the game behind it. Next, let's add an HBox container and also set this to full rect. Then we'll add a VBox container and set it to expand horizontally. We'll set our VBox container to centered and our HBox to centered as well. This will center all of our control nodes both horizontally and vertically inside of our menu. Let's add a label. This will be our menu's heading. We'll enter Game Over. Under Theme Overrides, let's select font sizes and make it nice and big. Under Colors, let's turn on our shadow. And under Constants, let's make the shadow more prominent. We're going to add 2 more labels and 2 buttons. One label to show our final score, another label to show whether that final score is a hide score, as well as 2 buttons, one to restart and another to quit. We'll want to make sure these are coming in as children of the VBox container, not the label. So let's select VBox container and add our nodes now. Let's call this score label. We'll call this high score label. And these will be restart button and quit button. For now, let's default score to score:0. We'll make high score label read new high score. And let's give the restart button its text and the quit button its text. While designing a very intricate game over screen is outside of the scope of this project, I want to do a few things to clean this up a bit. First, let's center both the score labels. Let's make the score a little bit bigger. And let's change the color of the high score label. If we'd like our buttons to look more like buttons and sit side by side, we can put them inside a grid container. Select VBox container, search for grid. Let's drag both of our buttons in here. And with them both selected, let's come into Layout and set a custom minimum width of 150. If we want them to sit side by side, we'll need to give the grid container 2 columns, and to center them, select the grid container and set the horizontal alignment to centered. The last thing I'd like to do is put a little separation between our buttons and our text because everything's feeling a little bit cramped right now. Select the VBox container and let's search for margin container. We can drag our grid container inside of our margin container. Then, with the margin container selected, we can come into Theme Overrides and give it a little bit of margin on top. Let's say 25 pixels. It may not be the prettiest game over screen that you've ever seen, but everything that we need is here. Let's rename this to Game Over. Let's save this in our menus folder. I'm going to get rid of this exclamation point because it feels too angry. And then with our root node selected, let's attach a script. I'm going to name it Game Over. Now that we have all the nodes we need, let's start wiring things up. First, we're not going to need any of this. Next, I'm going to select the 4 nodes that we'll be working with so that we can bring them in as onReady variables. I'm going to command click and set all of these to unique name. I'm going to drag in, hold Control before I release, and now we have our 4 nodes. I'm going to shorten the names to save us some typing. Because none of these nodes are using custom classes, we don't need to worry about typing as label or as button to cast them. Our code completion will be intact. Let's start by connecting to our 2 button signals. Select Restart, Node, and look for the pressed signal. We want to connect it to our Game Over script. Let's do the same with our Quit button. In a simple game like this, if we want to restart, we can reload our current scene, which we can do by calling getTree.reloadCurrentScene. This solution won't work for all projects, but in a single scene game like this, reloading the scene will reset everything. And to quit, we can call getTree.quit, which will close the window. It's worth noting that calling quit on something running in a web browser will have no effect. Next, let's set up our getScore function. We'll call this when the game ends to pass our score variable into the Game Over screen. Inside of our setScore function, let's set our score text equal to final score colon the score that we passed in, which we'll need to cast to a string because we're adding it to another string. Later, this is where we'll compare our final score to our saved high score and display the high score field if necessary, and also overwrite the older higher score. Now, let's return to our gameplay scene and look at how we can pull this in. You could include your Game Over screen and have it hidden by default, but I prefer to instantiate it as needed. Let's create a constant, call it Game Over Scene. Let's go into our menu, grab our scene, drag, Control, click, and release. I'm also going to create a variable called Game Over Menu of type Game Over. When we instantiate our Game Over scene, we're going to store it in this value. That will allow us to check whether a Game Over scene already exists, and if so, not spawn another one or recall the existing one. Now, let's come down to our onTail collided and check whether our Game Over menu is still null. If not Game Over menu, meaning if we haven't added anything to this variable, then we're free to instantiate a new one. Just like we did with our food, we're going to instantiate it and cast it to Game Over, store it in our Game Over menu, and add the child to our gameplay node. Since we're not actually tracking a score yet, let's go back up to the top of our class, create a score variable of int initialized to 0, and each time we eat a piece of food, let's add 1 to our score. Now, when the game ends, we can call our setScore and pass in our score. And there we go. We are seeing final score 7. However, you'll notice the game is still going. Let's fix that now. Going back into our Game Over script, to pause the game while the Game Over menu is up, we're going to make use of Godot's built-in notification method. Godot objects are pre-subscribed to these engine-level callbacks. The ones we care about are enter tree and exit tree. These notifications fire when a node is added to the scene tree or removed from it. The notification function receives an integer in the form of this what variable that corresponds to these more human-readable constants, in this case, notification enter tree and notification exit tree. If you've never seen a match statement, they work a lot like if-else blocks. This is roughly the same as this. In plain English, this will pause our game when the Game Over scene enters the scene tree by setting getTree.pause to true and setting that back to false when it's removed. There's one more thing we need to do in order for this to pause our game when the Game Over screen comes up. First, let's make sure we're in our Game Over scene. Let's select the root node, come into Process, and change Mode Inherit to Mode Always. If we don't do this, the Game Over screen itself will be paused as well, and we won't be able to interact with any of the buttons to restart or quit the game. Now we can save and test the game.
A few moments later.
Now when we crash, the game is paused. You'll also notice that our restart button is working, as is our quit button. Great. So our game over screen is working. Now we can repeat this process to create our start screen. Let's go to Scene, New Scene, Other Node, and again, search for Canvas Layer. Let's rename this to Start Screen, add our panel, and set it to Full Rect. Since our start screen will never be appearing over anything else, we don't need to change the modulation so that we can see through it. Let's fast forward through this part since we just did this for our game over screen. Now that we have our start screen set up, let's save it in our menus folder, and let's add a script. Again, let's drag in our references. We don't need our process, but we are going to use our ready function. Once we have our save game set up, this is where we'll find out what the highest score is and set it here. For right now, we'll just hard code a value of 0. And of course, let's wire up our signals. Our quit button is going to be the same here as it was in our game over screen. Our start button, however, is going to be a little bit different. Since our start screen is going to be responsible for loading our gameplay scene, we're going to need a reference to our gameplay scene. And because in our game over screen, we're using this built-in function to reload the current scene, we need to make sure that we use the built-in function change scene to packed in order to replace the current scene with a new scene. This method works fine for small to medium-sized games. For larger projects, you're likely going to want a much more robust scene manager that handles things like background loading, transitions, and passing data between scenes. Good news, everyone! Since I first recorded this, I actually made my own scene manager, and I'm going to link it right here. Now back to your regularly scheduled. Never mind. When we've been starting our project, it's been going directly into our gameplay scene. Now that we have a start screen, we want to go into our project settings. Under Run, we're going to want to change this from gameplay to start screen. Now, when we run our project, instead of loading the gameplay scene, it's going to load our start screen. And if we click our start button is going to load our game. And our game over screen is going to allow us to restart or quit. We're going to set things up so that if the player presses the escape key, it will pause the game and allow them to quit or return. We'll also set the game up to detect whether the game has lost focus, meaning the player has clicked outside of the game window, so that we can pause the game in that scenario as well. One more time, we're going to go to Scene, New Scene, find our canvas layer, add a panel. We do want this one to be transparent because it's going to show up over top of our game when paused. And I'm going to speed through this as well, since now we've done this twice. That's all we're going to need for our pause menu. Let's go to Canvas Layer, rename this to Pause Menu, and save it in our Menus folder. Let's add our script, grab our references. We don't need either of these. Let's wire up our signals. On the resume button, we're just going to call QFree, which will just remove this from memory. And the next time the pause menu is needed, we'll just recreate it. Actually, let's make this a restart button. Someone's probably more likely to want to restart from that menu than quit. So we'll just put our same reload current scene here. And the same as we did with the game over screen, we're going to leverage these notifications to pause the game. We have to remember to select our pause menu, and in the inspector, set our process mode to always so that we don't pause the pause menu. In our gameplay scene, we can use the notification function again to detect when the game has lost focus. Since there's going to be more than one way to pause the game, let's create a new function called pause game, and we'll declare that function down here. We're going to use the same technique of checking whether we've assigned something to our pause menu variable. If we haven't, we can instantiate our pause menu scene and add it to the scene. We can see this in action by testing our game and clicking outside the window. Now the game is paused. I can hit resume to replay, and we do have to go back into our pause menu and rename this restart. The last thing that we're going to do for this video,
Hey, listen.
when we rename this quit button, we broke this. So let's just re-pull this in. There we go. The last thing we're going to do is let the player call and dismiss the pause menu with the escape key. First, we actually are going to use our process function. So let's grab process here, and we're going to say if input action just pressed UI cancel, which by default is mapped to the escape key, we're going to queue free. And the other place we're going to need this is in our gameplay script. Anywhere in our process function, we can do the same thing, except instead of calling queue free, we're going to call pause game. Now, if I run this, hit start, and press the escape key, the game pauses. If I press the escape key again, it resumes. We'll start by creating a new script to manage our saved data. We'll go to Create New, Script, and this one's going to inherit from Resource. Let's create an export variable of integer called highScore, where we'll save our highest score. Let's also define a constant called savePath with the path to the file where we're going to store this data. This user:// is the default save location. The name you choose for the file doesn't really matter. We'll use Godot's built-in singleton, the resource saver, to call the save function, passing in this class, including our highScore variable, and the path to where we want to save the file. Let's create a new static function called load_create that will look for an existing save file and load it, or if one isn't found, it'll create a new one. We're going to make it a static function because that will allow us to call load_create directly from the saved data class rather than having to create an instance of it to call that method. This is all we need to do for our saved data file. To make sure that this save file is always available to us, let's come into our auto-loaded global file, create an instance of saved data called savedata, and in our ready function, let's call savedata.load_create and store it in saved data. This will ensure that the second our game loads, it will either pull down our saved file or it'll create a new one if this is the first time the game has been loaded. This is also all we need to do in our global file. Now, if we come over to our start screen, where we had previously hard-coded highScore, let's access our saved data. If we run the game, this shouldn't look any different because we don't have a high score yet. However, just as a quick test, we can set and save a new high score value, reload the game, and we'll see that it's now there. Running this will fire our temporary test code. Now if we reload, there's our high score of 10. To clear that out, we can come up to Project, open User Data folder, find our save file, and delete it. This will reset our high score to 0. Let's clear out this test code and add some logic to our game over screen to detect for a high score and save it if we set a high score. First, we'll check whether our score is greater than our high score on record. If it is, we're going to make sure that our high score display is visible. We're going to save this score in our high score variable, and then we're going to call save. If, on the other hand, our score is not a high score, we're still going to set our final score text, but the only other thing we're going to do is hide our new high score display. Let's test this out. As expected, our high score is 0. I'm going to collect 1. Now you can see our final score is 6, and we're getting our new high score display. If I restart and crash after 4, we're not showing our new high score, but we do see the correct final score. Let's quit and come back into our game over screen and make our panel a little bit darker because I think that final text is a little hard to read. And that's all we need to do to save our high score. But the player still doesn't know what their score is while they're playing, nor do they know what the high score is that they're trying to beat. So let's create a HUD to display that information while we're playing by going to Scene, New Scene, choose Other Node, canvas layer, as we've done before, we're going to add a panel. But this time, we're not going to set it to full rect. We're going to set it to top wide. Let's add an H-box. Also set it to top wide. And instead of begin, which will push items to the left, let's set it to end because we want our scores in the upper right-hand corner. Now we can add two labels. We'll default it to score:0, duplicate it, call this high score, and set this to high score. For consistency, let's set our color to something in the orange range, our high score color rather. And because this is looking a little bit cramped to me, let's add some margin containers. Let's select theme overrides, constants, and put a little bit of padding on the right. And for our high score, just so it's not touching the right side of the screen, we'll give that a little bit of padding as well. This will give us a transparent HUD. If we want the HUD to be an entire bar, we can give it a minimum height of 32 to make it fit nicely in our grid. With a visible background, now our text is no longer centered vertically. Let's select our margin containers, come back into our constants, and add some padding on the top. There we go, that looks pretty good. Let's name our layer HUD and save this in our menus. Now we can go back into our gameplay scene, click the link to add a child scene, search for HUD, and add it at the bottom, which is where we want it because we want this to be on top of it. Now, if we test our game, you'll see that our character does move under the HUD as expected, which might be what we want. However, this is a good opportunity to demonstrate the value of our bound system. If I don't want the character to show underneath the HUD, and I don't want food to spawn there either, we can simply grab our bounds, grab the upper left, and move it down one grid position. Now, if I replay the game, you can see we wrap just at the HUD. All right, let's finish up our HUD. We'll go back in here and add a script. Let's give it a class name, HUD, get our references, control release, and in our ready function, we can set our high score text. Now we're showing our high score of 6. Great. We don't need our process function, but we do need a way to update our score as we collect food. Now we can go back into our gameplay, grab a reference to our HUD. Let's remember to cast it to HUD. And every time we update our score, let's reference our HUD, update score, and pass in score. Now when we play our game, every time we eat a piece of food, the HUD updates. Okay, we are almost done. Before we wrap up this video series, I want to do a little bit of cleanup, and I also want to refactor this so that we can make use of a getter and setter function. We don't really need it, again, because this game is so simple, but in a more complex game, this design pattern is really helpful. So let's take a look at getters and setters. If I scroll back up to my score variable, instead of setting this 0 here, I can add a colon and add these two sub-definitions. This is our getter, which is the same as accessing that variable directly. It simply returns its value. And this setter function, which will accept a value, same as doing score equals whatever number, but then every time we set the score, it's also going to call our HUD.updateScore. And this is powerful because you won't have to remember to call HUD.updateScore every time the score changes. Imagine that this game also randomly spawned bonus items that only lasted on screen for a few seconds. If you collect them, you might get more than 1 point. When you do collect those, you'll be updating the score in more than one place. And then you would also have to remember to call HUD.updateScore. In this case, you can simply call score plus equals whatever value, and the HUD will automatically be updated regardless of where you call that from. Now that we've set up our getter and setter, we can come down here and we actually no longer need this line. Let's test the game again, and even though we're no longer calling that after updating our score is still updating in the HUD because our setter is now handling that for us. Before we finalize our game, let's do just a little bit of cleanup. I'm going to go back through and remove all of our print references. Going to tidy up some gaps. I generally like to have all of my variables together. So let's move these down here. I had paired them in that video with the constants so that you could see that relationship. I like to have my constants at the top, my export variables next, my onReady variables, and then all the rest of my variables at the bottom. It's sort of a logical order of operations for me. Constants are what they are. Preloading happens first. The export variables, in my mind, happen before the onReady because you're doing them in the editor. Then the onReady's fire, and then your garden variety variables are stood up at the end. Again, you don't have to do them in this order. Lastly, let's clean up our ready function. I'm going to put a space here to separate this code from all of my signal connection code, and I'm going to change this up just a little bit. First, I'm going to add this line of code here that will essentially force our snake to start moving immediately rather than waiting one full tick before it moves, and I'm going to get rid of that space. We could go through the rest of our files to do similar cleanup, but I will encourage you, when you follow along or take this project further, to find an organization system that seems logical and comfortable for you. With that, we've got a fully functional game with a score, a high score system, a pause menu, a way to restart, and along the way, we've covered more than a dozen common fundamental design patterns in Godot. Hey, you did it! Before you go, a couple of housekeeping items. First of all, congratulations. I hope you enjoyed that and feel more confident starting your own project. If you need help, please get in touch. This completed project is available on itch, which I've linked in the description down below. And for those of you who have written your own version of Snake, you should check out this video next. It includes 5 coding challenges that you can use to test what you've learned. If you've stuck with me for an hour, that's got to be worthy of a like and a subscribe. And look, if it's not, we can still be friends. Until next time, please be kind to yourself, be kind to others, and I will see you in the next video.